Thank you very much for allowing me to be here today. And I mean, just to make point of the fact that when I moved from IBM to the University of California, and I knew nothing about the world of research and funding and writing proposals, I'd never written one. The very first people that funded me were the Air Force, Office of Science Research, and the ONR, and they both have stuck with our program until today. And I'm incredibly grateful. It's not just so much for the funding, although that, of course, is wonderful, is the fact that when you really want to encourage graduate students to take very ambitious projects, they need to know that they'll be funded through their PhD. And there are very few agencies that will provide that type of support and encourage high risk and often quite a lot of failure. So part of me thought it'd be fun to come here this morning and just talk about our failures. But I only have 45 minutes. We have many more failures than successes. But honestly, I think without this type of funding, which is literally arguing for very high goals, it'd be very difficult to do what we've been doing. So I am very grateful. So with that type of introduction, let me just tell you what one area of research that the DoD has been very instrumental in driving for us, which until recently has been largely a material science effort and now is moving from science into technology, which is using solid-state materials for quantum information processing. So just before I begin, how many of you are physicists? And just how many of you have had quantum mechanics? That's fantastic. Okay. It's probably one of the few rooms in Washington where people have had quantum mechanics. So let me tell you what's sort of driven part of our science research, which is thinking about all of our technology today, which is based on classical electronics, moving charges around circuits. And we've become really, really good at manipulating these charges in extremely clean materials, building technologies with unbelievable fault tolerance. I mean, it's very rare for a device not to work in your machines. And when you look at what Intel has done alone and what they're doing right now in their fabs, I mean, they're literally building 5 billion transistors a second with silicon technologies. So the question is, can you harness this type of fabrication infrastructure to do something a little different? And the challenge we have as physicists and material scientists is to think about, can you look at materials at the level of individual electrons and individual nuclei for technology? Now, it's important to realize why that's so important. You know, after 30 to 50 years of tech, it's very hard to find single electron transistors. It's very hard to scale things down to the single particle level because at ambient temperatures, these electrons are hopping all over the place. It's hard to stabilize them. So it's been a big challenge, and a lot of experimentalists have been pushing very hard to just look at single particles to see what you could do with technologies. So the challenge is really to just watch them, build them, and control them very precisely, where at the level of single particles, I think as you all know, the dynamics are all driven by quantum mechanics. So if you can do that, it opens the door to lots of interesting applications. So our perspective is very different. It's that semiconductors are like people, and it's the defects that make us interesting. And while industry has worked very hard to get rid of all the defects in semiconductors, for classical technologies, what's a little ironic is for quantum technology, one of the most powerful applications is to put the defects back in. Because it turns out the defects in materials naturally trap individual electrons. And those, it turns out, can be examined much more easily than people guessed. And the quantum mechanics is much more robust than everybody anticipated. And that's driving a very exciting part of this field right now. So I'm very heartened to hear that almost all of you are familiar with quantum mechanics. And those who aren't absolutely need to be. So I've tried to develop, for the next 40 minutes or so, stepping through some very interesting scientific developments, rather than talk about the field in an abstract way, to really talk about some research projects that have been very surprising in what they've shown, and I think are given rise to both interesting science and tech. So to talk first about how rather remarkable it is that you can control an individual electron at room temperature, manipulate it at gigahertz frequencies, look at its quantum mechanical properties, and by doing so, has opened some interesting new device technologies based on geometry. So I had the pleasure of talking to some mathematicians earlier. And interestingly enough, some mathematical predictions in geometrical phase are now being used to build prototype devices. So it's a really interesting time for this area. It's a confluence of fields coming together to do some very different things. So I'll talk about that. How theory has been used to predict new types of materials where you can see these types of effects. Even commercial materials where people haven't looked before, but it turns out they work very well. And finally, some very recent work, also based on some theoretical predictions. Can you use magnets and magnetic materials to drive quantum phenomena? And this is a particularly interesting one, I think, to the ONR, because the Naval Research Lab for decades has been one of the leaders in magnetic materials. And now it turns out you can use these materials to manipulate quantum states. It's a surprise, it's very recent, but I thought I'd share that with you. So I hope that makes sense. So I wanted to just start with one or two introductory slides because it adds on to what Siobhan was saying about investing in people, which in this case are graduate students. And some of the areas in solid state physics began with a really surprise observation by some students in the lab that were actually funded by both the Air Force and the Navy to look at magnetically doped semiconductors. And the idea there, and industry was very interested in the time, was could you mix magnetic properties and semiconductor properties together to mix logic and storage? It's a really interesting science and technology goal. It turned out not to work so well. And when the students were trying to understand what they were seeing, they looked at materials that were in its natural state. They removed the magnetic materials. And in this example, they looked at commercial wafers of gallium arsenide. And it was a simple experiment. They put in a pulse of polarized light. They created billions of polarized electrons in these commercial wafers. They put on a perpendicular magnetic field and watched the states process around the field like a top. And the surprise was that at certain doping densities of these semiconductors, the coherence of these states that were put in a superposition of up and down could persist for really long periods of time. No one thought this could be possible. People thought quantum mechanical states were very sensitive to the environment. They would scatter quickly. They wouldn't live long. Turned out they lived for a very long time. And based on the doping density, when they were near metals, it would get very short. They were insulating, they would be short. But there was a regime where they would last a long time. It's a very big surprise. These were billions of electrons. It was at low temperature, very much a physics experiment. And the second surprise in these materials was that if you applied a little voltage, you could take these puddles of quantum mechanical states, either the spins of the electrons going up and down, and move them hundreds of microns through the material with surprisingly little dephasing. So hundreds of microns sounds pretty small, but on the scale of a device of a few microns, that's amazing. It means you could move them through wires in their quantum state without losing much of their quantum properties. Very big surprise, low temperatures, lots of particles. So this work went on. People began to try to understand what the origin was, and by going to wider band gap materials, all this physics was brought to room temperature. So these were commercial materials, zinc selenide, gallium nitride. This was a particularly interesting material because particularly at the time, which was in the mid-90s to 2000, these were just riddled with defects. So this was a terrible semiconductor compared to what was used in technology. About 1 million times the defect densities of what were used in devices. And despite the poor material, beautiful quantum mechanical properties could be created and maintained in those materials. So it meant we were missing something in this area of science about how quantum mechanics plays a role in real systems. So the challenge was, how could you get from millions of particles to just one? Because at the end of the day, these individual quantum states or bits will have to be put together to do something, either for sensing or communication or computation, right? So 3 pillars of a quantum technology. So lots of material techniques were used. Chemists began to make chemically synthesized nanostructures. This was work done at Berkeley, where in these small semiconductors, 1 electron could be optically created in each of these little dots, and put millions of them together, and sure enough, you could see these effects. They were not as big, but they were present at room temperature. And that got people to think, what else could you do? And this is a pretty interesting development in this field because, ironically, almost all of the origins of this field started also at the Naval Research Lab, which I'm not saying because I'm here. It's actually true. Where people began to do spin resonance measurements in materials like diamond for all different types of applications. Diamond's a semiconductor. It has arguably the highest thermal conductivity on the planet for a material. People have always wanted to use it in tech, but it's been hard to grow. And diamond has lots of defects in it, and I'm sure some of you have purchased a diamond. Yeah. Okay. And they have different colors because the different defects have different colors. Nitrogen makes it yellow, boron makes it blue. And they were trying to understand these defects and how they related to the structural properties of diamond. And what they found is that the lines were very narrow, and you could isolate single defects. So defect means there's a missing atom in a material, or in different parts of a lattice, it could be substituted. And it turns out, as I mentioned, these defects can trap an electron very strongly so that it can be studied even at and well above, hundreds of degrees above room temperature. It's very powerful. Based on the type of defect, like I mentioned in diamond, you can tune the wavelengths all over the place, from telecom frequencies down to the near ultraviolet. But because you can trap the electron, as I just showed you, the spin of that electron is a quantum state that can be controlled. That means you have a prototype quantum bit, one electron whose quantum state can either be sensitive to or be shielded from the environment. So it turns out these materials have very long coherence times of one electron, meaning this superposition of up and down can last for surprisingly long periods, orders of magnitude longer than people thought. You can optically control them. You can optically measure them. And because they're sensitive to the environment, it also means they could be extremely good sensors. And I'll show you in a little bit, you can actually put these sensors in living cells. You can use them for thermometers to measure electric and magnetic fields with extraordinary precision. So lots of opportunities are coming because of this ability to control the states. So I have a slide with a Hamiltonian, which I was initially worried about, but now I'm very comfortable about showing, and only because it's actually very simple. You can understand the quantum mechanics of these properties because it's a Hamiltonian with just 3 terms, and each one has a real physical meaning. The first is that these defects in a material like diamond, for those of you who are familiar with magnetism, normally to separate an electron going between spin up and spin down, you need to apply a magnetic field, right? The magnetic field creates a Zeeman splitting. What's interesting in these materials is that there's a lot of strain in the lattice, and the strain lifts that degeneracy automatically. So even with no magnetic field, you can address the spin up and the spin down state. So it's even easier. You don't need to do anything other than look at these quantum states to begin to explore them. And the natural splitting that comes from the strain is 2.8 gigahertz. And the reason I'm saying that is that's right in the telecom frequency. That's a microwave frequency. It's where all of your cell phones operate. It's a very easy frequency to control. You can tune it a little bit with an applied magnetic field if you want to. You can change these separating spin levels of a few megahertz per Gauss, so they're very tunable with refrigerator magnets, very low fields. You don't need much. As it turns out, in some of the dopants that come nearby, like in this case of nitrogen near a vacancy, there's a nuclear spin. And I'm not going to talk about this today, but you can use pulse fields to move the electron information into the single nuclear state and make a single atom nuclear memory. And that nuclear memory can last for a very long time. And you can come back later with an electron and extract the information. And it's important for me to emphasize it's the quantum mechanical information. So it's all of the information. So one nuclear memory, one atom, one nuclear spin can easily store 1 billion pieces of information. It's limited by how precisely you can read it. So with these types of quantum memory, storage is no longer an issue. In a cubic micron of material, you can store more information than the number of atoms in the observable universe. It's a huge amount of information. The problem is finding it. And that's where quantum machines can play a very important role. Okay, so my other slide, which is slightly physicsy, is these materials are often thought about as trapped atoms. So there's a strong link between atomic physics and solid-state physics, because these trapped electrons behave exactly like trapped atoms in a gas, very cold atoms. They're individual, very clean states where you take unpolarized light at very low powers, much lower power than this laser pointer. If you just illuminate a material like diamond that has these defects, and they all do, you'll excite an electron that will relax and end up in a spin-polarized ground state. Nature has been very kind about this. Literally unpolarized light. Just you point a laser, and if you are wearing a diamond, you could point a laser at it and you'll end up with nicely spin-polarized electrons. Not that you care about that, but you do. And because this strain creates this spin splitting between up and down at 2.8 gigahertz, if you apply microwaves, you can manipulate the state between spin up and spin down with extreme precision. And when you do that in the lab, if you just go online and you buy a piece of industrial diamond as an example, and there are lots of defects. This is an optical image of these little points or electron defects in commercial diamond. This is a wire that's put around it to blow up of this coplanar waveguide. If you apply this 2.8 gigahertz field to, say, that particular spot in the diamond, you have a microscope objective there and you just look at it, that's the type of data that comes out. Beautiful quantum mechanical oscillations of that spin between up and down, up and down, up and down. of that one particle. And it was this type of data that really transformed this area of physics. Because for decades, people have been trying to come up with ways to measure a single electron precisely with incredibly elaborate low temperature experiments. But this is done on the desktop with a microscope objective with a commercial piece of diamond. The experiment's about 1 or 2 square feet, and with a small piece of wire. So it transformed how people began to think about quantum control in solid-state systems, much easier than people thought. And these types of oscillations persist at room temperature, 400, 500, 600 Kelvin just fine. At the high temperature end, all the way down to 1 Kelvin just fine. So it's very robust. So quantum properties, turns out, can be pretty useful. And adding defects to material, not surprisingly, it's a lot easier than cleaning up the material. So if you go and you buy an expensive piece of diamond, thanks to the ONR, and although we worry sometimes about what the orders look like when you buy diamonds, and you actually create a mask with a bunch of holes and you shoot ions into the holes to create defects, you can create quantum states, tens of thousands of them. In this case, about a quarter of them actually work properly. But it does show a pathway to be able to think about building arrays of quantum systems for interesting applications. Now, there are lots of challenges here, how you link them, how you control them, how you read them. But there's a lot of interesting progress going on right now. But the exciting part is this is all addressable, and they're relatively easy experiments to do at this stage. So I want to show you a couple of examples of what you could do that are beyond the normal things. And the first is what I mentioned about geometry. So in the 1980s, some mathematicians had some very interesting theories about geometrical phase. So this sounds pretty abstract, although I'm sure not for mathematicians. For me, this is very abstract. And Barry and some of his colleagues in London had a pretty interesting idea, saying that if you took a particle and you somehow moved it around the right path in phase space, like a Mobius strip, if you start from one end and you come back to where you started, you may not be in the same place. You could pick up a phase. And it was an interesting math idea, thinking that phase could be information. But you're not actually physically moving the particle. In the world of semiconductors, you're moving its spin. And if you could move it around a certain path, you could have information, but you never move the charge. It's the ultimate low-power electronics. So our own group decided to try and pursue this to see if you could use one spin, see if this phase exists and what properties it might have. The idea is literally to control this one spin in the material, move it around the path on a sphere. So you keep the origin fixed, take the tip of this arrow and move it, and carve out different paths in space, and the path provides the information. Now, this is interesting science and math, but it has a very interesting application. Most devices today are sensitive to noise, and noise is because the energy levels of the device are changing. The gate speed of the device can jitter in technology. Those generate noise. This mathematical idea is a pretty interesting thing because none of those matter. The information is the path. If there's noise along the path, it doesn't matter. So if this exists, it's a pretty interesting idea to make a quiet technology based on a quantum mechanical effect, which is counterintuitive. You would think quantum mechanics would be sensitive to these things. This idea is that it's not. So just to make sure it's clear, what we're going to do is we're going to take the tip of a spin, move it from the north to the south pole, bring it back along a different path, and that type of orange slice is the information. Okay, and you can go around that path multiple times, adding more phase, go backwards, all sorts of things you could do. But the spin itself never leaves its position. And because these are quantum states, they're a little tricky to read. You have to actually, at each point on this path, you have to project their information onto a basis, some way to read it. So they're fairly labor-intensive experiments. But the nice thing about optics is you can now do these experiments by taking all of the technology that atomic physicists have used, but now use it in these materials. And what atomic physicists have shown is that when you have something called a lambda configuration, the energy of a particle looks like this, looks like the letter lambda, a split ground state and one excited state. If you choose one wavelength, you can excite one spin state to a certain point, one energy, one place on a sphere. If you choose a second wavelength, it will relax. It will go to another point on the sphere. You excite it, it will relax. But they showed if you could excite both simultaneously, which you can do today with phase-locked solid-state lasers, you apply both wavelengths at the same time to the same particle, you can create a superposition of these states that's called a dark state because it doesn't couple to any optical fields. So all that means is that by choosing the phase and the amplitude of two laser beams aimed at this one particle, you can put this spin anywhere you want on the sphere. It's a very elegant, but actually pretty simple technique that you can do today because of really nice, clean, phase-locked laser technology. So I'm just going to show you what happens when you do this. So on the left is actually some data taken from one electron spin. This was at 20 Kelvin, going from the South Pole to the North Pole and back. So it starts in the red path and then ends up in the blue, and for different wedge angles. So each one of these data traces, there's some phase has been added to make the orange wedge wider and wider. So this just means to show you can do this experiment. So what we're doing is literally doing this for different size wedges. So the idea actually can be done on one spin. And if you do this very carefully, this is the phase that's picked up from this one electron. So this mathematical idea actually does work. You can go through these paths multiple times and add phase. You can go clockwise and counterclockwise and remove the phase. So it really is a quantum mechanical effect where you can create and destroy information with one particle without moving it. So that's pretty neat. It actually works. And from the science end, that's very interesting. But from the tech end, the question is this sensitive to noise? And again, like adding defects, adding noise is not so hard in an experiment. So we added a type of noise called Uhlenbeck-Ornstein noise. It's a type of noise that's pretty common in devices. And what we did is we added noise along the path, and then for different wedge angles, different phases. And what you can see in this plot is the yellow circles are the shot noise limits of quantum detectors. So these are like state-of-the-art noise and good detector technologies. And this is adding noise. In this case, 8 degrees of noise. That's a lot of noise into a device. Most would have tiny fractions of a degree. No effect at all, which is remarkable. If you add noise perpendicular to the path, then you're changing the path, and sure enough, the noise has a big effect. So it means that you designed a quantum technology where the external noise would be largely in one direction. You could actually make a technology that's largely immune to noise. The other thing that's interesting from a mathematics end is in most types of technologies, the longer you average something, which tends to be a random walk process, the more noise is introduced in the process. In this idea, because the noise is driven by the time that you measure, normalized to the number of steps in the process, actually the longer you measure, the lower the noise. And you can actually do that in the lab and show the longer you measure, the noise just drops. So the reason I wanted to mention this isn't that it's so much esoteric, it just shows that quantum technologies behave very differently than classical technologies. And they offer some very interesting new directions, not just for platforms for science, but for applications in ways you might not think. Whoops. And one more note I wanted to make on this is this attracted the interest of a group of theorists who've been working in superconducting technologies, where they had come up with some ideas to make devices move more quickly. These were people working with both in university groups, but also with some companies, about how you could move quantum states faster and faster, beyond what's called the adiabatic limit, much faster than thermodynamics would let you do. So it's probably not worth going into great detail here, but the end story is that we tried their techniques with these types of solid-state systems, and they work just as well, where we could get a 300% speed improvement on how fast you move things around this wedge, almost to the speed of quantum limits. So in less than nanosecond timescales, you can get over 90% efficiency in these devices. So these are prototype examples. They're not devices. These are physics experiments. But this is just in the last few years, just to give you a sense of how quickly all this is going. And frankly, and surprisingly, how well it's going. Make sense? OK. I want to move to, these were examples in diamond, but you could step back like superconductivity and say, why diamond? You know, there should be lots of systems in which this worked and no one's looked before. So right before I left Santa Barbara, one of my collaborators and colleagues, Chris Vanderwall, and I got together, and we asked him if he could use some of his theoretical tools to try and predict, a little bit like genetic screening. When you looked at materials around the world, what other materials might have the same properties that could allow quantum technologies to exist? And he ran these codes for almost a year. And the first thing that came out of our theoretical work was about a half a dozen or a dozen materials popped up. And what was striking about these first ones on the list is these are all commercial materials. And we were very surprised because you can buy all of these. A lot of these are already used in tech, and suggested that these would be good quantum technologies. So we began to look at the first one, which is silicon carbide, which I may or may not need to say much about in this room, because it's one of the most popular high-power electronics technologies around. It's used in almost all avionics. We joke about it being the best of silicon and the best of carbon put together. It's because devices can work at very high temperature. So most Boeing aircraft, for example, run with silicon carbide. From a funding perspective, I should point out that the price of these samples is the same. These are the normal diamond samples that we actually grow in our own lab. They're a few millimeters. Diamond's extremely cheap to grow, no matter what someone might tell you in a jewelry store. It's grown from methane. It's the cheapest and easiest material to grow. The problem is you need to grow it on diamond. So this is an 8-inch silicon wafer, which you can, if you have a very convincing graduate student, they can get for free from a company by asking for a sample. It's easier to get a sample than to buy one because it's hard for them to sell you one. They're used to selling hundreds to thousands. But one lasts us for a very long time. And just to reiterate, it's used a lot for MEMS technology, accelerometers, right, airbag deployment, high power electronics. Any of you have solid state lights at home? LED lights, the nitrides are almost exclusively grown on silicon carbide for gaining technologies. And it's been pursued since the mid-1990s. If you look in the literature, these were random access memories that were done at Purdue with Cree as a research project by the DoD, in this case for satellite memories. And the point is people have gotten very good at crafting silicon carbide into, say, photonic bandgap structures where light and matter can be controlled at the nanometer scale. And for quantum systems, that's really important. We, for example, work on putting individual spins in cavities like this, where light and matter can be exchanged controllably, where when you look at the system, it's either light or matter, but it can be both, which in the quantum world is not so surprising. In the classical world, is very difficult to imagine. Okay, so I just want to show you that these theory predictions worked out beautifully in taking some wafers from Cree. So these were substrates used for lighting. The biggest problem in these experiments, there were too many defects. So we had to figure out ways to cut them back a little bit. And by looking at just some defects in Cree, I won't go into details, but it turned out that, sure enough, these quantum states were just beautifully evident. Silicon carbide grows in many polytypes, which just means that you can have beautiful single crystals in different forms. And in the z-axis, the spacing can be slightly different based on the particular stoichiometry. So that means you can build things out of silicon carbide, which is nice. It also means based on the symmetry of the lattice, you can have a material where all the spins point in one direction, or they have to choose one of 3 directions or 4. This is an example where it was one of 3 directions, and every one of them had beautiful quantum oscillations, and these were just 8-inch commercial wafers. So it was right. If you look very critically at this, if you're an engineer, which I am not, I'm in an institute of engineering, but I just masquerade as an engineer. But this is being recorded, right? I'm proud to be an engineer. But if you actually look at the magnitude of these oscillations, from a physics end, it's great, but it's a pretty small percentage of the whole signal. The lifetime of these quantum states turned out to be well over a millisecond, which was a very big surprise because silicon carbide is a pretty dirty material. There are nuclear spins all over the place. Nothing has been, there's been no effort to purify this or clean up the material. And yet, they're the longest lifetimes of any known natural material for quantum information. So it also means we're missing something from the science, and why does this work so well? Again, roughly 5% of the silicon are nuclear spins. So for a quantum state, it's seeing fluctuating magnetic fields all over the place. This shouldn't work so well. So we thought, but if you step back and think about how this field is progressing, even given the questions that are coming up, in the 1990s, this was work at the Naval Research Lab looking at spin coherence in materials like diamond on big ensembles. Then people began to purify the material using CVD growth. People began to control the isotopes to make better diamond. The lifetimes got longer. These are the lifetimes on the y-axis. And this is the commercial silicon carbide, okay, with no effort so far. So I think things are just going to get better and better and better as we learn more and more about the science, which is, already you can perform 10 million operations on these states before they decohere in this commercial material with no effort. So I say things are looking pretty good. Very recently, one of the students who spent a great deal of time understanding the interaction of light and the spin pointed out, this is being recorded, so I have to be a little careful. Anyway, the students are very bright, often brighter than their advisor. And this particular student pointed out that the experiments would work much better if you actually were to detect the light coming out at the resonance frequency. So he did that, and I showed you those oscillations, which were very nice, were just a few percent of the signal. Here they're over 95% of the signal. Same experiment, actually, just moving the detector. This looks almost like a trapped atom, but it's just one spin in silicon carbide. Beautiful quantum mechanical oscillations in this wafer with very high contrast. So things are just getting better and better and better and better, even to the point that we're beginning to understand why this is working so well. One of our theory colleagues at Chicago, Julia Galli, came up with an idea that if you began to mathematically model the interactions in the system through a first principles quantum calculation, she actually pointed out that if you have a geometry that have die vacancies where they're missing atoms periodically, you're better off if you put in some fill-up spins to stabilize the environment. Because based on this type of stoichiometry, identical nuclei can never be nearest neighbors, and a very small field polarizes the background. And she was able to model with virtually no adjustable parameters the data that we've been taking on these experiments. So what's sort of neat is now a predictive model is beginning to emerge to be able to predict quantum properties of materials to help guide all of these experimental efforts around the world. This is very recent and really, I think, very impactful result because it means there are probably thousands of materials that no one's even thought about because they've been ruled out because of these limits of spin interactions. Okay, one last thing I want to make before going to my final topic this morning is a sort of surprise that came out of these experiments as well. Another student who was understanding how the nuclear spins in this material were behaving was tuning the magnetic fields, tuning the energies, exploring phase space, and found that at certain magnetic fields, at room temperature, he could polarize all of the nuclei in this material, effectively 100% nuclear polarization. So I can't tell you how rare this is in nature. For people doing MRI, for example, in hospitals, you have these very large magnets, right, when you do an MRI image, and it's because the effective polarization, right, is a tiny fraction of 1%. That's what happens with MRI, very tiny fractions for imaging. So here, right, with a few hundred Gauss field, which is extremely low, you can get 100% polarization at room temperature. So this work was published, and while physicists like me were very interested in this for quantum memories, the major interest came from the medical community, which have been looking for high contrast MRI agents. And this is just silicon carbide, right? So you can dice this up and make small pieces of it. Very big surprise. You do have to illuminate it. And just to emphasize what a big effect this is, to get this type of effect in a material, you would normally have to be at microkelvin temperatures and to get these sorts of polarization states. So this is a very, very efficient effect. And it's because at the right magnetic fields, the Zeeman crossings between the electron and the nuclear spin overlap. And you get very efficient exchange. These polarized electrons, that are 100% polarized, flip their spins by flipping a nearby nuclei. They just exchange information. And they do it very efficiently at these fields, which are these fields. So we're working very hard with now some of the imaging groups at Chicago to try and use these as high contrast imaging agents in radiology, where we're doing some prototype experiments to polarize these and then inject them in systems, because now they're getting 10,000-fold larger signals than you would get before. There's still lots of challenges, but it's an interesting direction. I'm actually going to skip this. The very last topic I want to talk about, which is a third project. Were there any questions on this, by the way? Yeah? No? Okay, absorbed. The very last part is a very recent work, which I thought would be nice to mention here because it was also inspired by work from Gary Prins and others at the NRL who were studying spin waves in magnets. So magnetic materials have spin waves. You can have magnetic waves in materials. It's the basis of a huge amount of microwave technology. It's in your iPhones. They're used for mixers. They're used for all sorts of things. But the nice thing about magnets is people have been studying them forever, and the modeling is just fantastic now because they're devices. And there have been some very interesting theoretical ideas of that if you have magnetic materials with lines between them, can you begin to couple them with magnetic wires that have spin waves? And we thought, well, maybe what you could do instead is use these magnetic spin waves to control a quantum state. And so I'm going to just talk about a very recent, very simple experiment, because I think it has some interesting ramifications about how you can take a very thin film of magnetic material, have a wire, this is really an easy experiment, put microwaves through this wire, they will launch surface spin waves in this magnet, and what happens if you put a quantum sensor on it? Can this quantum spin see the spin wave as it approaches? And obviously it will, right? But the question is, what do you learn from this? And this was a project we gave to a new student, because we didn't think it would be a good way to learn about a lot of techniques, but maybe not the most exciting scientifically. And as is so often the case, you're usually wrong when you make these statements. Turned out to be incredibly interesting. Let me show you. So we started to use YIG. For those of you who might not be familiar with YIG, it's sort of the hydrogen atom of magnets. It's a garnet material. The spin waves in this material, if it's clean, can go many feet before they begin to damp. They're very, very clean magnetic materials. And we use nanodiamonds. And what we did is, I told you we grow diamond cells, but our students have come up with a very interesting technique to actually pattern the diamond and make small diamond particles. So each of these diamond particles is sitting on a substrate, is tethered with a small polymer bond. We can release them in a solution. And in each one of these particles are between 1 and 3 quantum states that have been engineered in the material by growth. So the idea is if you can release these, put them in systems, and they're little beacons that can emit the state of the quantum particle in different environments. So the idea is we wanted to place those all around this and see what was going on. So in order to do this in an interesting way, one of the nice things about our institute is there's a lot of discussion, and we're learning a lot. I'm learning a lot of chemistry. I don't know very much chemistry. I know even less biology. But I'm beginning to learn about the directed self-assembly in chemistry using polymers. And we approached one of our colleagues, Paul Neely, to see if we could use his techniques to pattern arrays of diamonds through a chemical synthesis method, meaning you decorate the diamonds, let the system self-assemble, and then end up with a membrane. A membrane of diamonds you can place on different materials. So not only does this allow you to place diamonds with a controlled structure, but it means you can actually use the same diamond, the same quantum state, pick it up and move it for different experiments. And because of the uncertainties in quantum mechanics, that's a very powerful tool. Okay, that's very hard to do in any other method. You need a way to grab 1 nanometer particle and move it. So this is an example of what the first efforts of this looked like using commercial nanodiamonds, not the nice ones I showed you. They take a long time to make. The commercial ones you can buy online. They're made through what's called a detonation technique. And that's exactly what it sounds like. They explode. It means the diamonds are just awful. They have different shapes. There's a lot of strain, but they're very cheap. So we use them. And I'm just going to show you the results in the last couple of slides because it was a very big surprise. So we put the diamonds on. We launched these surface spin waves. And this is the applied magnetic field, and this is the frequency. This is our 2.8 gigahertz. This is where the diamond quantum state should be. This is as we apply the field. This is what you'd expect to see as the quantum state change in energy. This modeling, if you can see here, these are the spin waves moving through the material, the purple and black. And you can see that this lower state intersects lots of spin waves. They should see them. We do this experiment, don't see anything. You see what looks like a big mess here. A lot of magnetic noise, very depressing. Student worked for a long time, used a few milliwatts of excitation, which is what you typically do in resonance experiments. Nothing worked at all. Very sad moment for us. But then the student did something that I thought was really brilliant. He did something that you would never do. Normally, as a student, you would increase the power. You basically would try to you would try and drive the system as hard as possible. And instead, what he did is he actually turned down the power. And when he turned down the power, it worked beautifully. In fact, he turned down the power 1,000-fold lower than anybody's used to look at quantum states. Unbelievably interesting results. So he dropped the applied power 3 orders of magnitude and saw these beautiful resonances as these spin waves were gliding through this quantum state. And there are 3 resonances here because these diamonds are pretty poor. and these spins are pointing in 3 different directions. So these are the different spins that are probing in one diamond. But it worked. But we didn't understand why it worked so well. So for a long time, we assumed that he was seeing stray fields from the experiment. This was not the spin wave, because how could it work 1,000 times better than it should? So again, that worked pretty well. And is often the case as well with faculty members who usually assume the student is incorrect, right? And as it turns out, of course, the student was completely correct. And he discovered something really fascinating, which is that you could couple spin waves to these quantum states with relatively little loss of information. So if you have an antenna and you have a quantum state, the field drops off as 1 over the distance. The farther you are from the antenna, the lower the signal, right? That's how antennas work. Putting this magnetic material nearby had no drop in signal. You could launch your signal here, the spin wave would carry it a very long distance, and it would be just fine with virtually no loss. So to prove that, he launched spin waves with different powers. So you expect these Rabi oscillations in quantum states to go as the square root of the power, and sure enough, it does. But it's magnetically driven. It's a spin wave doing this. The other thing he showed, for those of you that might be a little bit more mathematically inclined, is there's some very interesting pulse sequences that have been developed on quantum states to remove the effects from the environment, to prolong coherence. And their acronyms are named after the authors who did this. And it's very important for quantum technologies to enhance coherence by applying spins of different amplitudes and phases to try and drop the background noise compared to the quantum state. The point is, he actually ran these pulse sequences with magnets, and they worked very well. He could actually extend the coherence by applying spin waves at different pulses of different widths and amplitudes. And the point was to show that magnetism could control quantum states, just like RF fields. I think it's a very significant discovery. The really interesting thing is that it enables you to communicate between quantum states over much bigger distances than people thought. So just to point out again, this is 4 milliwatts in conventional driving. This is 1 microwatts using a spin wave. Same particle, same place. And if you look at the amplitude of the signal, it's 100 times stronger using the magnet. So what he did then is take this little membrane, pick it up, move it farther and farther and farther downstream to see how this worked. And what he found is that the enhancement kept growing and growing. The signal just never dropped compared to an antenna. So when he moved, in case, a couple of 100 microns away, which is a very big distance quantum mechanically, it worked beautifully. And this is well beyond the reach of photonics. It's well beyond the reach of traditional gating, but it works very well with magnets. So we think this is a very interesting new direction for this field, using ferromagnetism to control quantum states. So this shows you can sense and control. It's still not entangling, so it's still not going to be a basis for entangling states for computation. But based on the numerical estimates of the magnitudes of these effects, in principle at lower temperatures and somewhat smaller structures, you should be able to entangle quantum mechanically with magnetic materials, which is another platform for building quantum systems. So it's a very interesting and I think new direction for this field that could work out very well. I think the student has a very shining structure and future. So I wanted to stop here so we could talk a little bit. There are 3 topics I tried to broach this morning. The first is that the ability to control individual quantum states means you can try and study some very exotic things, such as quantum and geometrical phase for science and technology, which seems to work. It might lead to a type of technology that's noise resilient. We'll see. The fact that you can resolve quantum states now at the 95% level, and I should tell you as of a week ago, this is now 99%. So it's almost 100% quantum control in silicon carbide. Means you should be able to build nodes in quantum networks. And the Army Research Lab, for example, you may know, has been collaborating with us to drive a project to build a 3 to 4 node quantum system on a chip for encryption and communication. Coherence times are very long despite nuclei, and the theoretical predictions is this should be 100 times larger if you can clean up the material, which would be extraordinarily large and the largest node for ambient temperatures. And finally, I think this recent work with magnets is a very new direction, not just for entangling and communicating, but for sensing and being able to sense things farther away from the location of interest relatively easily, but there's still more work to be done. And finally, I should say, of course, that I don't do any of this work. It's done by an excellent group of students, and that's really the purpose of the funding. So while we need the laboratories, of course, the bottom line is that the DoD funding goes primarily to train these students. And in this area in particular, it's really important to build a national workforce of quantum engineers. It's a very interesting mix of training you need to enter this field. It's both theory and experiment, both physics and engineering, both computer science and electronics. It's very difficult to manage this properly, and we're trying, but it wouldn't be possible without this type of support. So thank you very much.